From Ubiquiti's product page for EFG, you can see Ubiquiti highlights the complete high availability feature. So the keyword is complete, which means it not only supports the shadow mode, but also automatic failover. So you can see in the note, the complete HA is closely related to VRRP. In this video, I used two EFG gateways. One was purchased by myself. The other one was sent by Ubiquiti for me to test the shadow mode. By the way, I have not received any extra documents or internal notes regarding the software implementation. So everything I'm going to show you in this video is based on my own research and investigation. In this Ubiquiti's help document regarding shadow mode, all the detailed step-by-step instructions were already given by Ubiquiti. So this video is not about how to configure shadow mode for EFG. Instead, we will look deeper to understand how it works. Now let's see the automatic failover from client's perspective. From the left side Linux machine, let me SSH to a UniFi switch, which is here, outside of this lab environment, in the WAN part. Okay, I'm in, so I can have interaction, right? Then in the right side, let me ping 8888. Okay, I will keep it running. So the difference between these two sessions is the left side is a encrypted TCP connection. From client perspective, it's using just one connection. That's it. And then from the right side, the ICMP packets for each individual ping, it has nothing to do with the ones before it and after it. They are different type of connections. So then from the lab environment, let me go to settings, control plane. If I go to console, you can see now the shadow EFG is ready to take over. Let me trigger a automatic failover by shutting down the primary EFG. Shut it down. Okay, from the ping session, you can see it hangs there because the automatic takeover is happening now. Okay, it's automatically resumed. It took about 60 seconds. Every time if I do the same testing, the wait time is different. Every time it was not very short. So this time it's 60 seconds. So now from the ping side, it's automatically resumed, which means the automatic taking over already happened. From the web UI, you can see it's restoring network. Yes, the console, the gateway is up and running, but it need to start the network application. Right? Everything takes time, but I can already carry out the regular network activity. From the console display, you can see now the original shadow gateway, the failover already activated, and the original EFG is showing offline. Then from the left side, let's see what happened to the SSH session. See, I can still do whatever I want. So the session is not dead. That's important because that's closely related to from backend what the system does when it takes over. Okay, so we already see the automatic taking over works in action. Now let's dig deeper. According to Ubiquiti's instruction for configuring the automatic failover, this red link from the part 2 of the primary EFG to the same part 2 of the shadow EFG, that's a must, a mandatory connection. This link is used to synchronize the configurations between the two EFGs. So I will use it as an entry point. Let me see what I can find for the traffic within this link. If possible, I can configure port mirroring to run Wireshark, right? But if you go to the EFG port manager, for example, if I choose a free port, for example, this port 3, if I go to menu for operation, I only have two options. Port mirroring option is missing, which means from EFG itself, you have no way to configure port mirroring. The only way left to me is to directly run Wireshark using the remote capturing. So let me show you. In the lower part of the screen for this Linux session, let me launch Wireshark, from the home screen, you have this SSH remote capture functionality. So let me click the config first. So I configure the primary EFG's IP address, the SSH port number. Here for authentication, I give the root credentials. For capture, this is important. Here for remote interface, I specify Ethernet 1 port. The reason is, remember we are talking about port 2, right? So internal name for port 2 is Ethernet 1. Then I want to use TCP dump. That's it. Save it. Then double click. See, what catches my eye is the VRRP. So let me filter on VRRP. You can see for every second from this strange IP address, it sends out a VRRP announcement to another strange IP address. Because VRRP is what Ubiquiti highlights on the product page for the EFG to support automatic takeover. These two IP addresses become my clue to find out what's happening behind the hood. By the way, if you pick a VRRP packet, you check the details, no matter how hard you try, you cannot find port information. The reason is VRRP uses the IP protocol number 112. Unlike what you are familiar with TCP or UDP, they have port numbers, right? For VRRP, there's no port number. It works differently. So that's why even from Wireshark, you can only see the IP addresses. So let me take this 169.254.254.2 as the clue. Let me SSH to the primary EFG. By the way, we can easily confirm which port has the IP address we are interested in. The Ethernet one has this IP address. Okay, now let me run netstat command. Let me see what processes are doing something using this particular IP address. This result reveals a lot of interesting information. See here, there's a process, it's called connection tracking daemon. The other one is called Keepalived daemon. Because I know these two tools are very widely used to support high availability in Linux world, and they are free, they are open source. No wonder Ubiquiti also chooses these two to support the HA for EFG. Now we have another clue, Keepalived and connection tracking D. Before digging deeper into those two components, let's talk about other processes we can see here. For Nginx and Node 18, they are used to run the network application. That's understandable. Then let's talk about the S-tunnel and DNS mask. S-tunnel is a proxy designed to add TLS encryption to existing client and servers which don't need any changes in the coding. They can support TLS. S-tunnel is used here is to encrypt the configuration interchanges between the primary EFG and the shadow EFG. Now I restarted Wireshark capturing and filtered the display to TLS. You can see from time to time, randomly, there will be packets from the primary EFG to the shadow EFG. Then in the network controller, if I go to the shadow gateway, click on it, here I can force a manual sync, right? Let me click on it and let's see what's the change in the Wireshark. See, right away I see a whole bunch of packets. They were the results of this sync now functionality. So this proves, yes, this S-tunnel TLS thing is related to the configuration sync. Okay, another interesting thing is about the DNS mask. You know, DNS mask is used by UniFi gateway to support DHCP and DNS, right? Why between these two EFGs DNS mask is needed? In Wireshark, if I filter on DNS, you can see some requests sent from the shadow EFG to the primary EFG. Of course, this DNS request is supported by DNS mask. It leads to an interesting topic. When the EFG is in shadow mode, what it is really doing? Does it even have internet access? To have that question answered, I need to somehow SSH into this shadow EFG. Based on previous discovery, we know for the primary EFG, it has a special IP address 169.254.254.2. And then the EFG shadow has a similar IP address ending with .3. But from the right side, try to SSH to that .3 IP address. Of course, it will fail because this client cannot directly reach out to that IP address. But it's not a problem. What I can do is I can first SSH to the primary EFG. Then use it as a jump board to jump to the shadow EFG. I SSH to the .3 strange IP address. Okay, see, I'm connected. Okay, I'm in. I am in the shadow EFG. That's exciting. Now let's see whether this EFG has access to internet. Let me ping Google. Yeah, it does. That's strange, right? So let me see what's the routing table. Unfortunately, this routing table doesn't explain why it can even access internet. I suppose there are some additional routing rules behind it. So let me run IP rule. Yes, see here, we have a special rule. It's using the IP route table 250. And to confirm, this one is really related to the internet access. For this EFG, we can use IP route get 8888. Okay, this explains how this machine can even reach out to Google. So it's via this IP address. Remember what's this? This is the primary EFG, right? Through this Ethernet 1 part. And yes, it is using this IP rule table. Yes, this is the .3, this particular EFG's IP address. If you want to see the details of this 250 table, we can run IP route show table 250. This is a very simple table. It simply says, okay, it's a default route, and you reach out to the primary EFG using this Ethernet 1 part. That's it. And this protocol PBR is simply telling you where this route is coming from. It's coming from policy-based routing because we are talking about VRRP. We are talking about a special scenario. So this is just informational purpose. Okay, we are clear about the routing for the shadow EFG. Okay, we have these minor topics cleared out. Now let's proceed with Keepalived D and connection tracking D. Those are the main topics for this video. Keepalived D is a routing software. It mainly supports two different things: load balancing and high availability for Linux system. For EFG, for the shadow mode, Keepalived D is used to support high availability, and Keepalived D's high availability is achieved by using VRRP. VRRP is used for router failover. VRRP stands for Virtual Router Redundancy Protocol. It's a protocol that ensures network redundancy by allowing multiple routers to share a single virtual IP address. Then go back to our lab environment. In the lower part, I show you two SSH sessions. The left one, we can validate the IP address. You can see it has Ethernet 4 is for the 1 part, and for Ethernet 1, it has the .2 IP address. This confirms it is the primary EFG, right? Then in the right part, if I run the same command, you can see it only has a .3 IP address for the Ethernet 1 part. It doesn't have one IP address. So this confirms the right side SSH is for the shadow EFG. Then in the left side, let me run the ps command to show you the Keepalived D instances. So we have two individual Keepalived D processes running. They have parent-child relationship. To show you that clearly, let me run ps3. This 2643 is the child of 2638. And if I go to a folder under run, it's called VRRP. You can see two process ID files, Keepalived D and VRRP Keepalived D. If I show the content of these two files, okay, so we can confirm, right? According to this tree, the first one is called Keepalived D. The second one is called VRRP Keepalived D. The second one, the one starts with VRRP, it is used to handle the VRRP specific announcement and reaction. If we go back to our captured Wireshark packets, if I filter on VRRP, you can see this VRRP announcement sent out from the primary EFG every second. This announcement is handled by the VRRP Keepalived. And another thing regarding high availability is about VIP, virtual IP. So think about it. During runtime, you have two physical EFG devices, but only one of them has the crucial gateway IP address for LAN. In our case, it's this BR0 for default network, and the IP address is this one, .1.1, right? So this is the VIP or virtual IP. Why is virtual? Because now this IP is pointing to this primary EFG, right? But if this primary one fails, this VIP should be automatically pointing to the shadow EFG because it should fail over to this EFG, right? This type of VIP functionality is also handled by Keepalived. So now we talk about two tasks for Keepalived already. One is the VRRP announcement. The other thing is the VIP, right? To understand how it works, we need to check its configuration. Under the same folder, run VRRP, you can see there is a file called Keepalived. This is the configuration file we want to focus on. Let me show it. Keep in mind, Keepalived not only runs in the primary EFG, but also the shadow EFG. So that's why I'm also going to show you the configuration file for the shadow EFG. So let's look at the global definition section. This directive, dynamic interfaces, it means, so for this red link, which is crucial for this HA setup, connected the Ethernet 1 of primary EFG and the Ethernet 1 of the shadow EFG. If this interface is down and then up again, the Keepalived service will dynamically bind the service to this link. This is what this setting means for allow IF changes. Then if you look at the right side, you can notice two additional directives about ARP. GARP here means gratuitous ARP. What these two directives are about is when this backup EFG, when it takes over, if the master EFG is down, it needs to let all the clients or the devices in the network know that now you guys need to refresh your ARP caches. Your .1.1 gateway IP address should be mapped to this new MAC address, which is the backup EFG's MAC address. So that's the gratuitous ARP message is for. So here it says it will send it 5 times and it will delay 3 seconds once the shadow EFG takes over, becomes the master EFG. When this backup node becomes master and claims the virtual IP, it's crucial that other devices update their MAC to IP mapping. Otherwise, traffic might still go to the old master's MAC address. That will cause packet loss or delayed failover behavior. So GARP, gratuitous ARP, resolves this by flooding the network with the new MAC to IP info. Okay, now let's move on to this section, VRRP instance. This is the most important section for the Keepalived settings. The first directive, state backup. This one may cause confusion because you can see the left and the right side, they are both backup. But we already know the left side is the master gateway, right? In fact, when they start up, there was a election process to elect the actual master. Based on what? Based on the other setting, the priority. So you can see the left side, the master has higher priority than the right one. So that's why the left one became master. That's how the election works. It's based on the priority. Then the next setting, the interface, Ethernet 1, that determines which link is used to do VRRP, which is crucial to failover. As you can see, this red link is hard-coded. is required by Ubiquiti's instructions to do automatic failover. Why it has to be this port 2 or Ethernet 1? Because it's hard-coded in the configuration files. Keepalived, the software, can flexibly configure whichever interface you want. But apparently Ubiquiti wants to skip the UI so that Ubiquiti hard-coded the interface, right? So I hope in the future Ubiquiti can provide a web UI to flexibly configure which port I want to use for the VRRP interface. But for now, unfortunately, it's hard-coded to port 2. Then here it simply indicate a number for the so-called virtual router. You can see in the right side, it has the same number. Then the advertisement interval 1 means every 1 second. So this is exactly what we observed. Every single second from the master EFG is sent out a VRRP announcement to the backup EFG. That's determined by the interval in the configuration file. Then the next one, preempt, is also very important. I won't show you the effect, but you may want to know, once the failover happens, the original backup EFG becomes the actual master EFG. Then if you fixed your original master EFG issue, for example, you start it up again, so the red link is established again. If that happens, this preempt setting indicates that an election will happen again. And because the original master EFG has higher priority, the original master EFG will become the new master EFG again. Basically, the router will fail back from the shadow EFG to the original primary EFG. That's determined by this setting, preempt. If you don't have this setting, even if you fixed your original primary EFG issue, you start it up, the failback won't happen automatically. Okay, and then here finally we see the VIP setting. You can see for the master and backup, the VIP setting is the same, which is the gateway's IP address .1.1, and the interface is the bridge 0 for default network. This section specifies the two peers, the master and the backup, what their IP addresses are. Keepalived supports multiple ways for the two nodes to communicate. Ubiquiti chooses the unicast way. So Ubiquiti assigns a distinct IP address to each node. It's specified here. From master side, you can see the master has this .2 IP address. The other side, the peer, has the .3. And if you check the configuration file in the backup node, it's the other way, right? That makes sense. So in this way, each node knows the other peer's IP address. Only after this, each node knows how to communicate with the other peer. At this point, we basically covered the major functionalities of Keepalived already. During runtime, the Keepalived in the master and in the backup, through the communication and the configuration, they go through the election process. They know which node is the master, which node is the backup, and then the master will send the VRRP announcement every second to the backup. If you shut down the primary EFG, the master, because the backup won't receive the VRRP announcement anymore, the Keepalived will elect the original backup node as the new master. But if you don't shut down the original master, you simply trigger the failover by unplug this red link. What will happen? Again, the original backup will be elected as master, and then the original master, because it cannot communicate with the original backup anymore, it will go to the fault mode. It won't be a master and it cannot be a backup because you don't have this red link, right? So once you re-establish this red link, the election will happen again, the failback will happen. The remaining section is about sync group. Here is mainly talking about connection tracking. So now we are switching to the second main topic for this video, which is the connection tracking. Connection tracking is very important to firewall. In UniFi network controller, if you go to security, for your firewall policies, create a new one. If you scroll to the end, you can see this setting about the connection state. If you enable the custom, you can see the different states. These states are part of the connection tracking. Linux kernel will track each connection's state so that, for example, when a traffic returns from the remote side, the Linux kernel still knows whether it's a brand new one or it's already a valid established connection or it's totally invalid connection. When it comes to high availability, when the failover happens, of course, you want the original backup node, the new master node, to know, to remember the existing connections so that the firewall policies will still apply. You won't have some unexpected broken connection, right? So that's the reason why connection tracking is an important part of the failover process. The idea is very straightforward. You run the connection tracking D in both nodes, right? And then during runtime, the synchronization will be scheduled so that the delta connections will be synchronized from the master node to the backup node, right? Before looking into the configuration details, let's see whether it really works in that way. In the right side terminal, let me SSH to a remote UniFi switch. And before I start doing that, in the left side, I'm in the master EFG. Let me run the connection tracking tool to list the current content of the connections. Let me filter out using the .15 subnet IP address I'm going to use in the right side. You can see even though now there are 2, 3, 4 flows are being tracked, there's none related to this IP address. Then in the right side, let me start the SSH session. Okay, I can have whatever interactions I want, right? So the SSH session is active and the connection is valid. So then in the left side, in the master EFG, let me run the connection track command again. See, this time I do see active connections. So the source IP address is the right side client and the destination is the remote, right? So that means currently in the master EFG, I do have entries about the .15 subnet connections, right? And we also know theoretically the master EFG should synchronize the delta connection information to the shadow EFG to the backup node in almost real time. Only if that's true, if the failover is needed, the backup node can take over and it can resume the connections. Theoretically, it should be that case. But is that really the case? Let's validate it. In the right side window, let me go back to the SSH session to the backup EFG. Let me run the exact same connection tracking command and only display this particular .15 subnet IP address information. See, strangely, nothing. That's weird, right? Because it seems if at this time, if the failover happens, the right side EFG won't be able to pick up that connection. That means my active SS session will be broken if the failover happens, right? But hold your thought. The reason is what we are doing now by running connection tracking command is only listing the Linux kernel connection tracking information. In fact, the connection tracking D is related to 3 different tables. One is the Linux kernel table for sure, which is actively being used by this Linux, right? But it also maintains 2 other tables. One is called internal cache. The other one is external cache. See this diagram? In the master EFG, whatever delta connections that need to be synchronized to the backup node, the connection tracking D will put them to the internal cache. Then the connection tracking D will synchronize the internal cache to the destination, to the backup node. Then the backup node will store those delta in external cache. Only when the failover happens, the system will put the external cache content to the kernel content. If you think about it, that makes sense. The reason is, let's just use this .15 IP address as example. This connection is valid from the master EFG perspective, but it's invalid to the shadow EFG because it's not really managed by this shadow EFG. So if we really see this connection information in the connection tracking, that's wrong, right? But when the failover happens and this backup node needs to take over, at that time, that connection is valid, right? The situation will be changed. Only at that time, the system will write the external cache content to the kernel. That's validated. So in the right side, in the backup node, we just run this command. It doesn't return anything, right? But let me use another command. Instead of using connection track, I use the connection track D, the daemon. I'm not running it as a daemon this time. I'm just using the existing configuration file, but I want to show its status. Let me run it. Okay, from the backup node perspective, now it has 0 active connection. Makes sense, right? Because it's backup node. But it does have 61 connections in the external cache. That's what synchronized from the master EFG. It's just waiting there. They will only be used if the failover happens. Let me run the similar command, but only show the content of the external cache. There will be 61 connections, right? Let me filter the result out by only using the .15 subnet IP address. Okay, we found it. This is for our SSH session. It's just waiting there in the external cache. It's not in the Linux kernel connection tracking table. I hope it's clear. There are 3 tables for connection track D to manage. Now we know the background information. We can look into the configurations. Now let's go back to the Keepalived D configuration. We were at this point, right? We have only one section to talk about. It is called VRRP sync group. Everything inside this group will be executed if the state of the node change. For example, if this EFG changes from master to backup, or this EFG changes from backup to master, or any of them change to fault, there will be a state change. This sync group will be executed. So let's see what will be executed. By the way, if you compare the master node and the backup node, you can see for this particular section, the configuration is exactly the same. So I will keep the right side one open, and in the left side, I will check different script from time to time. So see the 4 different actions. So notify means no matter what's the current new state, this one will be executed. Notify master means only if the new state is master, this one will be executed. So let's look into the first action. This script will be executed. Let me copy the script name. Then let me show that particular script. It's called VRRP update script. The only real thing it's doing is to call the Ubiquiti's client command. I assume the UI software will update the display on the user interface about the high availability status. At the end, you can see it put 0 to this failover trigger track, just to say I know the failover happens, so don't do it again. Let's start from scratch. Then if we check the right side script, when the node becomes master, let's see what will happen. It will run another script using parameter master. So in the left side terminal, let me show this new script. See, basically this script just does what we discussed, but we did it manually using command line. For example, if the node becomes master, see what it will do. It will run conntrackd using the way I just did manually in command line, and with parameter -c, which means it commit the external cache into the kernel table, just like what I mentioned in the diagram, this red arrow. Then it will do a -F to flush the internal and external cache because it's not needed anymore. This original backup node now is master node. All the old caches are not needed anymore, right? Then it runs the $R to resynchronize internal cache to kernel, and then -B to send bulk update to backup because it's the very first sync. So that's what it will do if it becomes master. I won't waste your time talking about other branches. So keep in mind that this VRRP sync group is only run if the node state is changed. It's not the one to schedule the synchronization during normal time. That is controlled in the connection tracking D's individual configuration file. So let me show you in the left side. In the same folder, there's a configuration file for connection tracking D. Let me show it. This is for connection tracking D's configuration. It configures its own IP address and the destination's IP address, then indicate the port 3780, and it will use Ethernet 1. So it's a pretty straightforward configuration. The only other thing I want to mention is the very last part. See, address ignore. It lists out the local host IP address and these two special IP address for the master and backup. So what it is saying is we are talking about connection tracking. It's related to your server's client devices in your local network. But these three IP addresses are internally used by the gateway itself. It doesn't make sense to synchronize the connection tracking status for these three IP address because even the failover happens, you don't really need any connection information about these three IP address. So that's why these three are ignored. And here we see this port number 3780. We can use it to go back to our captured packets in Wireshark. Let me remove the filter. Very common frequent type of packet is related to 3780. For example, this one. It's sent from the master node to the backup node, and it's using UDP, and it's using this part just like what we saw in the connection tracking D configuration. This is an example just during normal time. The two nodes are busy synchronizing the connection tracking information just to be prepared for the potential failover. Okay, so we are done with this connection tracking D topic. I know this video is already very long, but before ending it, I have one last thing to mention. You may already notice in my testing, to trigger a failover, I can simply simulate it by removing this red link from part 2 to part 2. Even though both EFGs, they are up and running, the failover will happen. In my opinion, that's not really necessary. It's too aggressive. There should be a mechanism for the backup node, the shadow EFG, to detect the master EFG is still active so that the shadow EFG will not be elected as a master node. How the system can do that? It can rely on this existing purple links because these two EFGs are supposed to be connected to the same switch. So theoretically, it does have another way to communicate to the other peer, even if this red link is broken. In fact, in the system, there is already such script. It is in this folder. Let me show you. It's this script, VRRP master guard script. Basically, just like the name suggests, it will do one more try before failing over. It will try to see whether the master node, the original master node, whether it's really done. So let me show you the script. Without this script, the system completely rely on the VRRP announcement. So if the backup node doesn't receive it, the failover will happen. But this script add another layer. After that VRRP validation fails, it will not fail over right away. It will do another try. First, it will ping the VRRP peer. But in our case, if we remove this red cable, of course, our VRRP interface will be broken, so this ping will also fail, right? It doesn't matter because there's another ping. See this ping? It will ping the LAN peer using the LAN interface. So theoretically, it's doable by pinging the master node by using this part, the LAN part, right? But the problem is based on the current configuration, the routing is not configured and the IP address of the master node cannot be reached from this backup node. That's why this script is not really used. I hope Ubiquiti can enhance it so that in the future this existing script can be used somewhere, somehow, just to avoid some unnecessary failover. Okay, this is the end of the video. Thanks for watching.